Imagine a beaker of pure water. The surface molecules are free to escape into the air, creating what we call vapor pressure. Now, watch what happens when we dissolve a solute into that water. These solute particles occupy the surface, physically crowding out the solvent and blocking its path to the air. To the escaping water molecules, it doesn't matter if the obstacle in their way is a molecule of sugar or a molecule of salt. The physical displacement is the same. Because the effect relies strictly on how many obstacles are present rather than what they are made of, we call these colligative properties. They depend entirely on the number of particles, not their chemical nature. This physical crowding leads us to our first specific property, the relative lowering of vapor pressure. Since fewer molecules can reach the air, the pressure above the liquid drops. This creates a mathematically predictable relationship that allows us to calculate exactly how the solution's properties will change. We track this change using the mole fraction of the solute, x2. The relative drop in vapor pressure, the pressure of the pure solvent minus the solution, divided by the pure pressure, is exactly equal to that mole fraction. By expanding that mole fraction, we get a ratio of masses and molar masses. To keep calculations organized, solute variables are orange, marked as W2 and M2, while solvent variables are blue, marked as W1 and M1. In dilute solutions, the number of solute moles is so small compared to the solvent that we can ignore it in the denominator. This simplification leaves us with a clean, workable ratio of mass to molar mass. Take example 1.6. We have a pure benzene vapor pressure of 0.850 bar. After adding 0.5 grams of solute to 39 grams of benzene, the pressure drops to 0.845. Plugging these into our formula allows us to solve for the unknown M2, giving us a molar mass of 170 grams per mole. By measuring the physical drop in pressure, we can successfully determine the exact molar mass of molecules we can't even see. This graph shows how vapor pressure relates to temperature. The top curve is the pure solvent. Notice that the solution curve sits lower. To reach the atmospheric pressure required for boiling, the solution must be heated to a higher temperature than the pure solvent. This increase is the elevation of boiling point. This change in temperature, ΔTb, is the product of the solution's molality and a solvent-specific constant called Kb. To find molar mass, we expand the molality term. Since molality is calculated per kilogram of solvent, we include a multiplier of 1,000 to ensure our units work correctly when we use grams. Try applying this to example 1.8. We have 1.80 grams of solute in 90 grams of benzene, with a Kb of 2.53. Pause the video and see if you can calculate the molar mass before I reveal the answer. If your math was correct, you found a molar mass of 58 grams per mole. The boiling threshold climbs in a calculable proportion to the solute concentration. That same drop in vapor pressure forces the freezing point of the solution to decrease. Note the order of the variables here. For boiling, the solution has the higher temperature, but for freezing, the pure solvent freezes at a higher temperature than the solution. To keep our ΔTf value positive, we must subtract the solution temperature from the pure solvent temperature. Whether we are heating the solution to boil or cooling it to freeze, the physical presence of the solute particles is the mechanism driving these temperature shifts. To calculate this depression, we use Kf, the cryoscopic constant. On your exams, these constant values are provided for the specific solvent mentioned in the problem. Let's look at one more application. In example 1.10, 1 gram of solute in 50 grams of benzene lowers the freezing point by 0.40 Kelvin. Using a Kf of 5.12 and our expanded molar mass formula, we can calculate a final result of 256 grams per mole. This summary matrix compares all three properties we've discussed. It includes the base definitions and the expanded formulas used for molar mass calculations. You may want to take a screenshot of this for your revision. Mastering these three derivations allows you to solve nearly any numerical problem involving molar mass and phase changes in this chapter. We have one property left to cover: osmotic pressure. Subscribe to Gyanen classes for our upcoming lesson on how to master that final piece of the puzzle.